Hi guys, today I'm going to show you a beautiful question which is the mechanical equivalent of Snell's law in optics. Let's go. A rod of mass m lies on a horizontal table with friction. The rod is hinged to point O and can freely rotate. The y-axis is the boundary between the regions with friction coefficients mu1 and mu2. Let θ1 and θ2 be the angles between the rod and x-axis. Calculate the amount of work E required to rotate the rod from θ1 to θ2 at a constant speed. Assume that the applied force is along minus x. Show that E is minimum when mu1 sine θ1 equals mu2 sine θ2. Find this minimum energy in terms of the parameters mu1, mu2, θ1, and θ2. Alright, just to remind you what Snell's law in optics tells us, it gives a simple formula between the angles of incidence and refraction for a beam of light passing through two different and transparent media with different refraction indices. N1 sine θ1 equals N2 sine θ2. Now back to the problem. The total work done is calculated by E, or work, is the integral of force times the differential element of displacement. And it is the amount of work done in medium 1 to rotate the rod in region 1 plus the amount of work done in region 2 R2 to rotate the rod. The differential element of displacement is given by ds equals dx e hat x plus dy e hat y. Because of the rotational symmetry of our problem, it is better to work in polar coordinates. X is equal to r cosine theta and y is r sine theta, and r is the radius of rotation, which is the distance from O to the center of mass. The force vector has two different values in region 1 and region 2. It is given by F equals minus mu1 times n Ex in R1 and minus mu2 n times Ex in R2. Because R1 and R2 have different friction coefficients. Therefore, energy is minus mu1 n Ex dot dx Ex plus dy Ey plus integral in R2 minus mu2 n Ex dot dx Ex plus dy Ey. Ex dot Ex is 1 and Ex dot Ey is 0. So energy simplifies to R1 minus mu1 n dx plus minus mu2 n dx in regions 1 and 2, which is minus mu1 n delta x1 minus mu2 n delta x2. You can see that this horizontal vector is delta x1, this delta x2. So delta x1 is minus r cosine theta 1, and delta x2 is minus r cosine theta 2. The negative signs here is because the vectors point to the left. E is minus mu1 n times minus r cosine theta 1 minus mu2 n times minus r cosine theta 2. Mu1 n r cosine theta 1 plus mu2 n r cosine theta 2, which simplifies to n r mu1 cosine theta 1 plus mu2 cosine theta 2. Now, given the displacement angle delta, we're gonna minimize energy with respect to this constraint. Delta. A well-known method for solving such a simple optimization problem is using the Lagrange multiplier. I give you a short recap. For a function of n variables, like f of, let's say here we have two variables and we let x and y. Given the constraint g of x and y, we want to optimize f subject to g equals 0. We form the Lagrangian function, which is L equals f minus lambda. G, in the case of extremum, like minimum or maximum, we must have the gradient of L equals 0, or partial derivative of L with respect to x and y, both have to vanish. We box this recap. In our problem, the Lagrangian function is L equals E minus lambda times delta, which is nr times mu1 cosine theta 1 plus mu2 cosine theta 2 minus lambda, which is a constant, times pi minus theta 1 minus theta 2. In this case, the partial derivative of L with respect to theta 1 must be 0, and the partial derivative of L to theta 2 must be 0. We have partial derivative of nr times mu1 cosine theta 1 plus mu2 cosine theta 2 minus lambda partial derivative of pi minus theta 1 minus theta 2 respect to theta 1 must be 0, minus mu1 and r sine theta 1 plus lambda equals 0. Mu1 sine theta 1 equals lambda over nr. In the same way, partial derivative of the Lagrangian with respect to theta 2 is equal to 0, minus mu2 and r sine theta 2 plus lambda is 0, and mu2 sine theta 2 is equal to lambda over nr. We name this equation 1 and this equation 2, and finally from 1 and 2 we have mu1 sine theta 1 equals mu2 sine theta 2. And we name this constant kappa. We want to calculate the minimum amount of energy, which we name by E mean, which is equal to nr mu1 cosine theta 1 plus mu2 cosine theta 2, given that the term in parentheses has its minimum linked to kappa up here. On the other hand, we have sine delta equals sine pi minus theta 1 minus theta 2, which is just sine theta 1 plus theta 2. And this is equal to sine theta 1 times cosine theta 2 plus cosine theta 1 times sine theta 2. Sine delta is kappa over mu1 times square root of 1 minus kappa squared over mu2 squared plus kappa over mu2 times square root of 1 minus kappa squared over mu1 squared. Kappa over mu1 times mu2 square root of mu2 squared minus kappa squared plus square root of mu1 squared minus kappa squared. Now A mean is equal to NR times square root of mu1 squared minus kappa squared plus square root of mu2 squared minus kappa squared. And from above formula for sine delta, it simplifies to NR times mu1 mu2 sine delta over kappa. So let's summarize what we did. We calculated energy as a function of two variables, theta 1 and theta 2. We minimized energy subject to the constraint delta as a fixed angle of rotation. And we finally arrived at the equation, which is the mechanical equivalent of Snell's law in optics. And from this formula, we calculated the minimum of energy in a nice or